There's a certain attitude that particle physicists tend to take when it comes to their experiments. Smash first, ask questions later. When it comes to the tiniest particles in the universe, there is a lot that we still don't know. So physicists study them using particle accelerators, huge machines that get particles like protons or electrons moving almost as fast as the speed of light. And then they smash them together and physics happens. Very explodey physics. And sometimes the researchers can't predict what's going to come out of the reaction. Instead, they have to work backward, looking at the data and using math to figure out what the heck just happened. Which is why, in September, physicists from the Technical University of Vienna announced that they think they've identified a whole new kind of subatomic particle, because they did some new math. The particle is called a Glueball, which is somewhat surprisingly a pretty accurate name. It's a particle of gluons, the sticky particles responsible for keeping an atom's nucleus from flying apart. Now that is a weird thing, because this particle doesn't contain any matter. It's made up of pure force. And if they can confirm this discovery, it'll be another big piece of evidence that the standard model of physics, the current understanding of how physics works, is in fact right. You might remember the Higgs boson, the main particle that gives matter its mass, which physicists confirmed not too long ago using the same working backward method. They bashed together some particles and then sifted through the data. It can take years to analyze all of that information, and new insights crop up long after the particle smashing is over. In the case of the Higgs, scientists knew exactly what to look for, but they had to analyze years' worth of data before they could confirm their discovery. With Glueballs, though, they're not even sure what the thing they're trying to find looks like, though they do know that they're made of stuck-together gluons. Now, normally, gluons are the things that hold quarks together. Quarks join up to form protons and neutrons, the basic components of atoms. So no atoms without protons, no protons without quarks, and to stick together, the quarks need gluons. That's because the protons in an atomic nucleus are all positively charged. If it were up to the electromagnetic force, those charges would repel each other and the atoms would never form. The protons can all stay inside the nucleus because they have the strong force to keep them there. The strong force is a fundamental force, meaning that we describe it separately from the other fundamental forces like gravity or electromagnetism. It's more than 100 times stronger than the electromagnetic force and many, many more times stronger than gravity, but it's mostly important on the scale of an atomic nucleus. Each proton or neutron in the nucleus is made of 3 different quarks held together by the strong force. The strong force holds together not only the 3 quarks that make up the proton, but the quarks in the other protons as well, so that electromagnetic force doesn't send them flying apart. Every force has a particle to carry it, known appropriately as a force carrier. Force carriers have no mass. The one for electromagnetism, for instance, is the photon. The same goes for the strong force, which also has a massless force carrier, which is, you guessed it, the gluon. That's what gluons are, and that's where the name came from. They glue quarks together. And gluons are definitely a thing. Researchers discovered them in 1979 using the Petra particle accelerator in Germany. But as far back as 1972, physicists were using math to show that gluons might have an odd property, the ability to stick to each other, forming a glue ball. 43 years later, we still haven't been able to prove they exist. But scientists really want to, because glue balls are predicted by the standard model, the best explanation we have for how particles and forces behave. Almost all of our understanding of science is based on the standard model, so it's kind of important to make sure that it's right. And there's a lot of evidence that it is right, like when we discovered the Higgs boson, which the standard model said we should. Until then, there was a chance that the standard model was totally wrong about how mass works, and if it was, we'd have to rethink a lot of science. So since the standard model tells us that glue balls should exist, researchers are looking for them as another way to confirm that our science isn't totally off track. But it's not like glue balls occur in nature. You can't just walk outside and pull out a powerful microscope and find one in a tree. But the standard model does tell us that there are a few different ways to make them in a particle accelerator, like by smashing together a proton and an antiproton, which is exactly like a proton, just negatively charged. I mean, don't try this at home or anything, but that sounds easy, right? Trouble is, there's a lot of stuff that comes out of these glue ball making reactions, and it's hard to tell what's what because we don't know exactly what we're looking for. Things that seem like they could be glue balls have been showing up in particle accelerators for ages. But nothing's for sure because we don't know some of the properties of a glue ball, like how much mass it has, for example. And yeah, the idea of a glue ball having mass is strange to think about in general because, like we said earlier, none of the individual gluons that stick together to form the glue ball have mass. And when you add together a bunch of things with 0 mass, you got 0 plus 0 plus 0, 0, right? Wrong. You don't, because of a weird property of energy. It is related to mass by a little equation you might have heard of, E equals mc squared. And it turns out the energy that's holding all those gluons together in the glue ball, that translates to mass. We just don't know exactly how much. To make matters worse, glue balls aren't stable. You couldn't, pick up a handful of them. They would just flit into existence and then right back out a moment later. And when you do create a glue ball, it causes quarks and their opposites, antiquarks, to just materialize. And whenever a particle and its opposite interact with each other, they both get annihilated, and the blast of energy from a quark and an antiquark coming into contact with each other just blows your glue ball into smithereens. So how do you find a glue ball if you can't observe one directly? Physicists have to put on their Sherlock Holmes deerstalker hats and deduce its existence from the traces it leaves when it's destroyed. They look at the data from the experiment, and if any of it looks like it could be a sign of an unidentified particle, they do the math to see if that particle would match what we know about glue balls. Which is why every so often candidate glue balls turn up in scientific literature. For the most promising ones, there's usually a dozen or so papers arguing for or against its glue ball hood. Two of these are the catchily named F0-1500 and F0-1710. We've known about both of them for a while, discovered in various particle accelerators over the years. We just don't know what they are or whether one of them could be a glue ball. 1710 is about the right mass to be a glue ball, even though we can't be sure what mass they should be. We can estimate it, and 1710 fits the description. There's a problem though. When that mystery particle decays, it produces a variety of quarks known as strange quarks. From everything we know about the math of glue balls, we thought when the gluons interact with each other, they'd make all kinds of quarks with no bias towards the strange ones. But that's where Anton Rebhahn and Friedrich Brunner, the physicists from Vienna, come in. They changed the mathematical approach to thinking about glue balls. Ordinary garden variety quantum physics tells us that glue balls should exist, but it's not very good at predicting how they decay in a particle accelerator. That's why there's been so much back and forth over which candidates are glue balls. So instead of using the more conventional math, Rebhahn and Brunner decided to use a different, more theoretical model, one that includes gravity with the other forces in its description of glue balls. The mathematical model that they used isn't universally accepted yet, but it might turn out to be a lot better at predicting glue ball decay because their results were a lot more specific. When they crunched the numbers, they found that it actually kind of made sense for 1710 to produce those strange quarks, even if it's a glue ball. But the finding isn't quite enough to definitely confirm 1710 is a glue ball or to rule out the other candidate, 1500. For that, we need more data. Researchers need to make more of this 1710 particle and see if the patterns of its decay matches what the new math predicts. Luckily, it is fantastic timing because other particle accelerator experiments around the world may be able to give us more data very soon. Rebhahn and Brunner say specifically that they're keeping an eye on some experiments going on at CERN, the Swiss lab that includes the Large Hadron Collider, the most powerful particle accelerator in the world. They're also waiting for the result of an experiment using an accelerator in Beijing, which should be coming out within the next few months. With these clues, the first confirmed glue ball discovery could be much closer than it's ever been before, and researchers will be looking. The game, as they say, is afoot. Thank you for watching this episode, and thank you for sharing in the excitement of science with us. One more thing I want to share with you is my friend Derek Muller's Kickstarter project, SNATOMS, the Magnetic Molecular Modeling Kit. This is not a paid endorsement or anything. I just really like these, and it's awesome, and I want people to know about them. You cannot construct a glue ball with them, but you can make water and all kinds of organic compounds and see the energy of molecular bonds as they happen. We'll put a link in the description to the Kickstarter. It's only going on for about another week. Check it out and have some fun.